Picking up with lesson 12.6, we're going to look at two amazingly powerful tests that are going to allow us to tell if series are absolutely convergent, divergent, or in some cases, allowing us to need to know further analysis in determinate cases. The ratio test. The ratio test is phenomenally wonderful for series that alternate, or perhaps like our example 2, might involve negative terms, not necessarily alternating. Wonderfully, they could even apply to positive term series as well. But look, if you take your n plus 1 term inside of sigma, divided by the nth term, keep this an absolute value, take your limit as n goes to infinity. If this limit arrives at a real number that is smaller than 1, and by the way, 0 is okay, you could arrive at 0, then the series is absolutely convergent. Remember what we were talking about in our first video. Absolute convergence means that our series converges when you put absolute values around the argument of sigma. But that also means that you will converge without absolute value. You can say, and therefore the series converges without absolute value as well. You get both thrown in. By way of comparison, for number 2, if your limit as n goes to infinity of your nth plus 1 over your nth term in absolute value, if that limit is larger than 1, or if that limit arrives at positive infinity, the series is divergent. And we do refer to the original series. The original series without the absolute value will diverge. The third possibility is to say that that ratio in absolute value, if that limit arrives at 1, the test is inconclusive. We'll have to use another test, go about other means to determine if we have convergence. This test is the most frequently used test in BC Calc. I'm circling here. It's wonderful. It's great for formulas involving exponents and factorials. It's really not so great for algebraic formulas. Let's just say inside of sigma, you'd have 2n plus 3 all over n squared minus 1 or something like that. Such a situation really would not be helpful to use the ratio test. You'd see that you'd actually arrive at a ratio of 1. So that's what I mean when I say algebraic. But let's see this in action. For number 4, state whether this series converges or diverges. And, the ratio test is definitely preferred because you can see our n is raised up as an exponent, and we also have n factorial. Our a sub n, of course, is going to be negative 1 to the n plus 1 times 3 to the n over n factorial. Very nicely. Our a to the n plus 1 is actually going to be bumping everywhere where we see an n. Every single time we see an n, replace that with n plus 1. So we'd actually have n plus 1 right up in here, plus 1. We'd have 3 to the n plus 1. Down below, we'd have n plus 1 factorial. And by the way, this n plus 1 for the power, if you think about it, that's going to become n plus 2. Okay? So here's our n plus 1 term. Here's our nth term over here. The ratio test is saying, look, take the limit as n goes to infinity of that n plus 1 term divided by the nth. And that will be, plugging all that in, you can see our n plus 1 term was negative 1 to the n plus 2 times 3 to the n plus 1 all over n plus 1 factorial. We're going to divide that, make a nice long division bar. Down here we would have negative 1 to the n plus 1. Here's our nth term. That's 3 to the n all over n factorial. This is all in absolute value. And I guess what I want to point out to you is, of course, when you have absolute values here, it's as if these negative 1s these expressions involving -1 are going to be inconsequential. The absolute value will guarantee there are no negative values remaining. So in essence, we can even drop our absolute values now, simplifying, knowing that n itself is always going from 1 to infinity. It's guaranteed to be positive valued. So we've got our top fraction here. That's 3 to the n plus 1 all over n plus 1 factorial. And dividing by a fraction is the same thing as multiplying by its reciprocal. So we can multiply by n factorial over 3 to the n. Now I hope you know that 3 to the n plus 1 and 3 to the n, this is a number of 3's multiplied together n times. This is a number of 3's multiplied together n plus 1 times. These will cancel out. You'll just have one more 3 remaining up on top. Now with the factorials, hope you remember that if I gave you something like 5 factorial, we could write that as 5 times 4 factorial. I'm going to do that down below. Even though I'm not knowing specifically what n plus 1 is in the moment, I'll say this is n plus 1 times n factorial. Very nicely, you can see that the n factorials cancel. So my limit as n goes to infinity is going to be 3 all over n plus 1. And of course, as n becomes very large, 3 over something unbelievably large is going to go to 0. Now if we look back on our little table, when our limit would be 0, like in this instance, that's very clearly less than 1. So I can say by the ratio test, and that's really like a little proof that we're writing out right here. By the ratio test, this original series, I won't put absolute value around it, I'll just write it as it originally was written. Right here, this is absolutely convergent. But remember that absolute convergence means that we are therefore convergent even without absolute value. When you converge with absolute value, converging absolutely, you'll converge even without absolute value. So we know this problem does converge. One more test, and this test is not nearly as frequently used, but it's very, very similar to our last test, the root test. Let's just say that you have a formula where inside of sigma, you have a formula raised up to an nth power. And it would be very helpful to eliminate the nth power by taking an nth root. Of course, an nth root would cancel an nth power. Well, if we've got this infinite series, if we were to take the nth root of the absolute value of a sub n, and if we arrive at a limit value that is less than 1, your series is absolutely convergent, and that means you converge without absolute value as well. If by way of comparison, you take your limit as n goes to infinity of the nth root of the absolute value of n, you get a value L which is greater than 1, bigger than 1, or even going to infinity itself. The original series is divergent, even without putting absolute value around it. Finally, just like with our ratio test, you're going to see great similarities between the criteria of the ratio test and the root test. If this limit arrives at 1, the test is inconclusive. So again, the telltale sign that you'd like to use the root test is when you see a formula and you notice, oh my goodness, I have formulas that I've seen so many times before in earlier sections, but now we're bumping everything up in addition to that to an nth power. If it would be very helpful to eliminate that nth power, the root test would definitely be a good choice. So we're going to take the nth root of the absolute value of this a sub n, and we have 2n plus 3 all over 3n plus 2. all bumped up to the n, and this is all an absolute value. And again, I guess what I'm trying to tell you is an absolute value is really going to render any expression with -1 to a power to essentially be canceled out. If you are at +1, you'll remain at +1. Absolute value makes a -1 turn back to a +1. And then we could say, well, then we don't need our absolute value anymore. 2n plus 3 and 3n plus 2 are all positive, and so is n itself. So the nth root of an nth power, beautifully and very simply, will cancel out. And you'll have 2n plus 3 all over 3n plus 2. Then, using n behavior, you can see that the plus 3 and the plus 2 are really inconsequential as n gets super big. 2n over 3n essentially cancel out to 2/3, and that's less than 1. So I can say, by the root test, this original series, -1 to the n minus 1, and here's 2n plus 3 all over 3n plus 2, bump it up to the n, is absolutely convergent, meaning it converged in absolute value, and is therefore convergent. It's convergent even if you don't put absolute value around it. So there you have it, two very helpful tests for convergence. Especially on the AP exam, the ratio test is without a doubt the most frequently used test on FRQs by far. So hope things are going well. Best of luck to you.